This problem involves an array shifting algorithm. We're asked to write a method called remove zeros that takes an array of integers as a parameter and that moves any zeros in the array to the end of the array. In this example, there are 3 zeros in the array before the method is called, and we can see that those 3 zeros have been moved to the end of the array. We're told that we're supposed to otherwise preserve the order of the list, so for these non-zero values in the list, they have to appear in the same relative order in the array after the method is done executing. We have lots of examples here, arrays that have a bunch of zeros, a single zero, nothing at all, no zeros at all, and an indication in each case of what the array is supposed to look like after the method is done executing. I've set up a JGrasp file that has each of these different cases in it, so we'll be able to use that to test our solution. And I have some simple testing code here that reports what's in the array before and after we make a call on the remove zeros method. Remove zeros takes an integer array as a parameter. It's not returning anything, which is why I've put void here for its return type. So our task is to fill in the code here that gives us an algorithm for the remove zeros task. There are a lot of ways of approaching this problem. One way, for example, is to think about the zeros themselves. So we could imagine going through the array until we find a zero, and when we find a zero like this, we could shift everything to the left by 1 to fill in that gap. That would be an approach that works, going through, finding all the zeros, shifting everything that comes after. There's a few tricky cases that we'd have to deal with in writing that code, but it would work. The problem is that that would lead to a fairly slow solution in certain cases. Like look at these arrays that have tons of zeros in them. We're going to end up doing a whole lot of shifting here. Look at this one, for example. We end up with just the values 1, 2, 3, 4, and then all those zeros. So do we really want to do all of that shifting here in order to end up with a result like this? It seems like there should be a faster way, and in fact there is. The way that I want to explore this is to imagine that we have available to us a second array that's just as big as the original array, a temp array in which we can store an answer. So in my code, I'm going to imagine that we have an integer array called temp, which is a new integer array that has the same size as the original array. So this is a temporary array we can use to keep track of our answer. And how do we do it then? Well, think about this case. This array has 10 values in it. 7 of them are non-zero. So 7 of these values would have to be copied into our temporary array. Here's a picture of what that would look like. Those 7 non-zero values have to be copied into our temporary array. To accomplish this, we can basically scan through our original array, traverse over the original array, looking for those non-zero values. So this is a case where we can use our standard traversal code for an integer variable I starting at 0, I less than the length of the array, I plus plus. And what we want to do is to look for the non-zero values. So if the next list I is non-zero, if it's not equal to 0, then what we want to do is to move that value into the temp, copy that value into our temp array. So we'd want to set temp sub some index to that list I that we're looking at. And that's basically how we would solve this problem, is for each of the different values in our original array, if it's non-zero, we copy it into our temporary. So what do we need to set this question mark to in order to get the right copying to go on? A simple case would be if we could just say temp I gets list I. Turns out that's not going to work. That's going to do a straight copy. 0 goes to 0, 1 goes to 1, and the algorithm begins in that way. But you can see that once we start encountering zeros, here list 4 is going to temp 3, a difference of 1. Here the list 7 element is going into temp 5, so the gap gets even bigger as we see more and more of these zeros. So it's not going to be as simple as just using an I here. We need something else. So how do we know where to place the next value? If you think about it, you'll realize that it's important to keep track of how many things we've placed in our temporary array. How many non-zero values have we seen so far? So that's going to be something that we want to count as we go through. So we want an integer count that we could start at 0 to keep track of how many non-zero values have we seen. Initially 0, and then each time we've seen a new non-zero value, we're going to increment our count here. Think about how we could use that count. Count is initially 0 before we've seen anything. Then when we see this very first value, notice that it goes into index 0 of the temporary array. After we've stored it, we would increment our count to be 1, and then notice that the next value goes into temp index 1. We would increment our count to be 2, the next value goes into temp index 2, and so forth. So it turns out that that count is actually what we want to use for the question mark. May seem a little bit odd that I do it in this order with the count being incremented afterwards. That has to do with the zero-based indexing. Think about the case, for example, when we've put 6 different values into the temp array. Because of zero-based indexing, the 6 values are in elements 0 through 5. So our count would be 6, but we'd have values in elements 0 through 5. But that means that the next one, the 7th value, goes into temp 6. So that count is always letting us know the next spot where we would end up putting something in the array. So this is in fact the right index to use. This will fill up our temp array in an appropriate way. But we weren't asked to make a temp array. We were asked to change the original array. So how do we get these new values that appear here to get back into the original array? You might imagine that we could say list is assigned to temp and hope that that just does a mass copy for us. But that's not how it works in Java. If we said list is assigned to temp, all we'd be doing is taking this local variable of ours and resetting it so that now it's referring to that second array. So it doesn't change the contents of the array. It would just change what array the list variable is referring to. So if we want to get all of these contents of the temp array back into the original, we have to write a loop. We have to traverse over the temp array and copy those values back. So instead of doing this, we'd have another traversal loop. We'd say for int I starting at 0, I less than temp length, I plus plus, and we'd want to set list I to be temp I. So here we really do want the copying that just goes I to I. We want all those values in the temp array to go back into the original list. You might wonder whether we could maybe stop early. Maybe we don't have to copy everything. Maybe we only have to copy the non-zeros. But in fact, we have to go that far because there are values here that weren't 0 in the original array. There's a minor point about this that's worth understanding, which is the temp array gets filled up with the non-zero values, but what about these other values that we never end up assigning in the temp array? So we assign these 7 non-zero values, but we never set these values here in indexes 7, 8, and 9. That works because when Java constructs the array initially, it initializes the entire thing to 0. So we got a little lucky in this case that we were asked to be moving zeros. If we were moving something other than zeros, then we would have had to assign these values of the array to give them an appropriate value. But in this case, we end up having the zeros here because they were there when the array was first constructed. So this is a solution that actually works. Let's go ahead and compile it, and we can run it just to verify. But if we take a look and see this array that has our initial example here, the 3 zeros have been moved to the end, the other 7 values are here in their original order. We'd want to look at each of these different cases and make sure that it's doing the right thing, but in fact this is a correct solution to the problem. So this is a way to do it. But even this is not the best way to do it because of the use of this temporary variable. In general, if we don't need extra storage, we don't want to have to use extra storage. If you wanted a simple analogy, suppose that these were mailboxes, that a company had 10 different mail slots, and they've got various pieces of mail in these different mailboxes, and some of them are 0 because these are people who've left the company. This person doesn't work for the company anymore, and that's why that box is empty. this person doesn't work for the company, the box is empty, and so forth. Suppose that they asked you as a worker for the company to shift the mailboxes down. So move these 19 pieces of mail into that mailbox here. And so they wanted you to compact the mailboxes so that all the empty ones are at the end. And if your response was, well, I can do that, but you have to get me an extra set of mailboxes. I need 10 brand new mailboxes so I can use that as a temporary storage place for the mail, and then I'll copy the mail back. I'll shift it back again. They would say that you're crazy. You don't need to have an extra set of 10 mailboxes to solve this problem. Why don't you just move these 19 bits of mail back to mailbox with the index of 3? Why do you need an extra set of mailboxes in order to make that work? So there's an insight into this problem, which is that we don't really need the temporary. In a sense, we can use the array itself as the temporary. So we want to do something like this. We want to do it with a single array, but where the value that's in index 4 ends up being shifted into index 3. This value that's in index 5 gets shifted to the index 4. The value in index 7 comes down to index 5. The value in index 8 comes down to index 6. And it really is almost as simple as just getting rid of the temporary array. So we won't need to initialize a temporary array. There won't be any copying back when we're done. But instead of setting temp count to list I, we set list count to list I. We copy back into our own array. And that way we don't need to use a temporary. So this is shorter code, and it ends up being more efficient in terms of not requiring that extra storage. But we do run into a bit of a problem here. So this one does have a problem that we didn't have before. If we go ahead and run it, it'll be pretty obvious when we look. So in this case, if you look, you can see, well, wait a second, what about the 3 zeros at the end of that array? Well, we can see that the first 7 values are correct, but then we have this 720. And that's not so surprising. That's because, unlike the case with the temp, where we had these zeros at the end that were just initialized when we created the array, we end up with this 720 at the end. That's the problem, is we have the 720. So once we've assigned the first 7 mailboxes, we're set for those. But these last 3 mailboxes have to be manually reset to be 0, just to make sure that we've done the right thing. So we do need a little bit of extra code here to make this one work. So we need an extra for loop. We want an integer I to start where this other one left off. Well, where did this other one leave off? Count tells you that. Remember that count was the index of the next place to put something. So for example, in this case where we're shifting 7 things, so we end up with 7 non-zero values in the array, and sure enough, element 7 is the first element that should be set to 0. So we want to start this I at count. We want to start where we left off before, and otherwise it's like the standard traversal. We let it go to the end of the array, doing an I++, and all that we do inside of here is to set list I to 0. So a little bit of extra code to do that, but still a more efficient solution than using the temporary, because it doesn't require the extra space, and it also will run faster because we don't have to do this 2-step process of copy into the temporary and then copy back. Now we have our 7 non-zero values with the zeros at the end, and we have our various test cases. We'd want to verify and make sure that they all work, but in fact they do. This is the solution to the problem that ends up being fast, and it doesn't require the use of extra storage. So this is a nice efficient solution to this particular problem.